Hello and welcome to another Control Systems tutorial with me, Richard Pates. Today we're going to learn about our first method of control system design, that of state feedback. A state feedback controller can be designed in the very special situation that the entire state of a state space model of a system is available for measurement. Unfortunately, this situation doesn't arise very often in practice. However, the principles underpinning the method of state feedback control extend far beyond this application and will lay the foundations for future, more advanced methods. Today, we will learn how to design a state feedback controller to meet two basic objectives. The first objective will be that of pole placement. The location of the poles of a system have a huge impact on how it responds to reference inputs, disturbances, and noise. By designing a state feedback controller appropriately, we can move these poles into more desirable locations and hence positively influence the behavior of the system. The second objective will be that of step input tracking. We will learn how to design a pre-filter so that in steady state, the system will perfectly track a step input. This will mainly be used to introduce the concept of step input tracking. In future lectures, we'll consider far more advanced and better design methods for this goal. The setting for today's lecture is the following block diagram. This block diagram captures the dynamics of the basic feedback configuration and consists of three main parts. The first major component is naturally the system that we wish to control. That's what's captured by this block here and all of the surrounding signals. U is, of course, the controllable input. D is a disturbance and may correspond to, for example, load disturbances to the system or unmodeled dynamics or unknown initial conditions. The signal on this arrow is the measurable signal. Since we're in the state feedback setting, the signal that we can measure is the state X, which is why we've denoted it X here. These measurements may be subject to noise, as indicated by N. Finally, Y denotes the outputs of the system of interest. The second major component is the control system that we wish to design, and again this is typically reserved two blocks, this block here and this block here. For simplicity, we'll focus exclusively on the design of the bottom block and just assume that the top block is equal to 1. That is, we'll design state feedback controllers for pole placement by simply picking this matrix K here in the block diagram. The final component is the pre-filter, and this is concerned with the tracking of references. The reference signal is denoted by this signal R, and typically we wish the output Y to follow R. We're going to design a gain matrix K pre to achieve this goal. But now on with our first objective, that of pole placement. Whenever we have a pair of signals in a block diagram, say U, the control input, and Y, the overall output of the system. By simplifying the blocks that lie in between these two signals, we can always arrive at a single transfer function, T of S, which will describe the relationship between U and Y. If we take the previous block diagram as an example, if K is equal to 0, so we have no feedback, this will simply correspond to the open loop plant. So K is equal to 0. The relationship between U and Y is given by P of S, the dynamics of the open loop system. However, if the controller is not equal to 0, the transfer function that we will end up with here will change, and this is typically referred to as the closed loop transfer function. We can get quite a lot of insight into how Y will respond to various inputs U by considering the poles of the transfer function in question. Roughly speaking, the output Y is given by a sum of contributions where we have contributions from each of the individual poles, and the location of these poles determines roughly how that contribution will look. Now, this is typically visualized by plotting the locations of the poles on the complex plane, as shown in both the figures on this slide. In particular, the real part of the location of the pole corresponds to exponential growths or decays in its contribution to the output. So if the pole location has a positive real part, this is associated with exponential growth in the output. And if it's negative, this corresponds to exponential decay. This is why poles in the left half plane are associated with stable behaviors. In contrast, the imaginary part of a pole is associated with oscillatory behaviors. If the pole lies on the real axis, then the pole contributes no oscillatory behavior, and the greater the imaginary part, the higher the frequency of oscillation. So if we just take this pole here as an example, this pole has positive real part and non-zero imaginary part, so it might contribute a component of the output that would look something like this. So an oscillatory behavior that is exponentially growing. However, if we look at, say, this pole, it has negative real part and no imaginary part. So this will contribute a component that is purely decaying in an exponential fashion, something like this. One of the big advantages of introducing feedback control, in this talk the gain matrix K, is that we can move the locations of the poles of the open loop system. So when we consider the relationship between U and Y with a controller that's not equal to 0, the locations of the poles will change, and we can use this to our advantage. In the next few examples, we're going to see how to design this matrix K to, say, push this pole here, which corresponds to a bad, oscillatory, unstable behavior, into the left half plane, say to this location here. And this is the essence of the pole placement problem. We've determined the location of a set of target poles and design a state feedback compensator to move our open loop poles to that set of pole locations. But where should we place the system poles? Unfortunately, there really isn't a good general answer to this question. Any choice of pole locations will always have to be supported by detailed robustness analyses and simulations. However, a useful rule of thumb is to use the pole locations given by the so-called Butterworth polynomials. The Butterworth polynomials are a set of polynomials of increasing order that are additionally characterized by a parameter omega c. The first three Butterworth polynomials are indicated on the right here, though we can have a Butterworth polynomial of whatever order we like. These polynomials have the nice property that their zeros are evenly spaced on a semicircle in the left half plane, which has radius omega c. This is illustrated here actually for the fourth order Butterworth polynomial, which we can see because there are 4 zero locations. The key point to observe about these polynomials is that we may push them further and further into the left half plane by simply increasing the value of omega c. We're going to use this by designing a state feedback compensator K so that the denominator of the closed loop transfer functions of our system are equal to a Butterworth polynomial of the appropriate order. This means that the location of the closed loop poles will be given by the 0 locations of the corresponding Butterworth polynomial. And therefore, by increasing omega c, these pole locations can be pushed further and further into the left half plane. As we said before, pole location is really just a heuristic for good behavior. You have to check other performance and robustness measures, but this will serve as a good starting point and is certainly sufficient to illustrate the principle of pole placement. In order to actually be able to perform pole placement, we need the following 2 key insights. The first is that if the state space model of the open loop system is controllable, then Under the state feedback control law that we've been considering, the closed-loop system poles are given by the solutions to this equation. This is useful because this term involving the determinant, well, this is just a polynomial. And so this means that the closed-loop system poles are given by the zeros of a particular polynomial. Even more importantly, the coefficients of this polynomial depend on both the matrices A and B, but also the state feedback matrix K, which we're free to choose. If we make this a little bit more explicit, expanding this determinant will give us a polynomial of the form a0, s to the n, plus a1, s to the n minus 1, and so on, where the values of these coefficients will depend on a, b, and k, and therefore by choosing different values of k, we can change the values of these coefficients. This couples in very nicely with our second key insight, which is that if two polynomials have the same coefficients, they have the same zeros. This means that if we can choose the values in our state feedback matrix K so that the coefficients in this polynomial are equal to the coefficients of their corresponding Butterworth polynomial, then the closed-loop system poles will be given by the zero locations of the Butterworth polynomials and hence lie in the Butterworth configuration. This will all become far, far clearer when we actually do some examples, so let's just get on and do that. Okay, so what do we have to do? Suppose that the open loop plant is described by this transfer function here with the following A and B matrices. So this is just another way of saying that the state space model for the open loop system is described by x dot is equal to ax plus bu. And we actually saw the system with precisely these A and B matrices in the lecture on reachability and controllability. It was one of the examples we considered where we found out that this pair was in fact controllable. So let's just bear that in mind. And it says, design a state feedback controller to place the closed loop system poles in the Butterworth configuration with this value of omega c. So let's deal with that first. Well, since our system is controllable, we can directly apply our two key insights from the previous slide. So we know what we need to do is solve the equation determinant si minus a minus bk is equal to a Butterworth polynomial of an appropriate order. So what order a Butterworth polynomial do we need to put in here? Well, that depends on the order of this polynomial, and the order of this polynomial can be determined from the size of the matrix A. Since A is a 2 by 2 matrix, this means that this will be a second order polynomial, so we need to match it to the second order Butterworth polynomial. So what was that? That was s squared plus the square root of 2 omega c s plus omega c squared. This was the second order Butterworth polynomial, and this will simplify to give s squared plus root 2 times root 2, so 2s plus root 2 squared, so plus 2. So our objective is to pick the matrix K so that this polynomial is equal to this polynomial, or more specifically, the coefficients of this polynomial match the coefficients of this polynomial here. So, well, let's just do it. So the first thing we need to do is work out what this matrix is, and then we'll know what to take the determinant of. So let's write that out. So the first term here is S times the identity matrix. So that is just SS 0, 0, like so. And from that we subtract A, which is 1, 4, 3, 2. And then we take away BK. So B is 1, 0. now we need to work out what the dimensions of K are. So we know that the matrix that will appear here, so the product BK, has to have the same dimensions as the matrix A. So this product has to give a 2 by 2 matrix. And from that, we realize that K must have 1 row and 2 columns. So the matrix K has 2 entries. Let's just call them K1 and K2, like so. So this is the matrix that's inside the determinant. Let's just simplify it a little bit. So what goes in the 1, 1 position? Well, that's S minus 1 times K1. So S minus 1 minus K1. And now the 1, 2 position, 0 minus 3 minus 1 times K2. So that's minus 3 minus K2. 2, 1 position, 0 minus 4 minus 0 times K1. So that's just minus 4. And the 2, 2 position finally is just S minus 2 minus 0 times K2. So just S minus 2. So the matrix inside the determinant is given by this. So in order to create this polynomial, we just need to find the determinant of this matrix. So let's do that. Well, the determinant is given by the product of the 1, 1 entry and the 2, 2 entry, sorry. So that product minus the product of the 1, 2 and 2, 1 terms. So what do we get? That is S minus 1 minus K1 multiplied by S minus 2. So that's the 1, 1 multiplied by the 2, 2. And we subtract from that minus 3 minus K2 multiplied by minus 4. So this polynomial is our determinant polynomial, and we just need to match the coefficients of this polynomial with the coefficients of our Butterworth polynomial here. So to do that, we need to just simplify this and collect terms. We've run out of space here, so let's just move things all the way up here and expand out this polynomial. So we're going to have to expand the term here on the left and the term here on the right. So starting with the term on the left, well, we've got S squared minus 2S. So S squared minus 2S. And then we've got minus 1 times S. So minus S plus 2 minus S plus 2, and then minus K1S plus K1. So, plus 2K1. So minus K1S plus 2K1. So that's the leftmost term, and from this we subtract the expansion of the right-hand term. And so what's this? This is simply minus 3 times minus 4, so that's 12, and then to that we add 4K2. So we're getting there. Now we just need to collect all the coefficients. So let's start with the S squared term. So we're just going to simplify this and collect all the coefficients together. So the S squared term, well, we've only got one of those, so that's just S squared. And now we collect all of the terms that depend on S. So there we have minus 2S, we have a minus S here, and we have a minus K1S. So that's going to be minus 3 minus K1. And now we just collect everything that's left, so the term that doesn't depend on S. So what is left? Well, we've got a 2. We've got a 2. This was a K1. So 2, we've got a 2K1, and then we've got a minus 12 and a minus 4K2. So plus 2 minus 12. that's minus 10 plus 2k1 and minus 4k2. So after a lot of algebra, we've determined that this polynomial in the determinant is given by this thing here, and to finish things off, we just need to compare coefficients. So we can use that to determine k1 first. So the first coefficient, or the coefficient in front of the s term in our Butterworth polynomial, is 2. So we can then use this here to determine that minus 3 minus k1 is equal to 2. And that implies that k1 is equal to minus 5. And now we do the second, do that again, but with the constant term. So we know then that minus 10 plus 2k1 minus 4k2 is also equal to 2. And so what does that tell us? Well, we know k1 is equal to minus 5, so that's minus 20. So we pull that over onto this side, and this gives us 22. So minus 4k2 is equal to 22. And that tells us that k2 is equal to minus 22 over 4, which is just 5.5. Minus 5.5. And, well, that's the answer to the first bit. The state feedback controller given by k is equal to minus 5 minus 5.5. So this state feedback matrix will place the closed loop poles in the Butterworth configuration with this value of omega c. So that deals with everything except for this final pesky part of the question, which asks what other pole locations are possible. So to answer that, we just need to investigate this polynomial a bit more, because we know that the zeros of this polynomial give us the pole locations, and we'll just investigate where we can put them by picking different values of k1 and k2. But we've run out of space on this slide, so we'll take a fresh one. But remember this polynomial. So what other pole locations are possible? Well, one of our key insights was that the closed-loop pole locations are given by the solutions to this determinant polynomial. So determinant si minus a minus bk is equal to 0. So the solutions to this equation give you the pole locations. And on the previous slide, we computed what this monster was equal to, and we found out that it was equal to s squared plus, and then we had minus 3 minus k1 s, finally, plus minus 10 plus 2k1 minus 4k2 is equal to 0. So the question boils down to, by varying k1 and k2, what locations of solutions to this equation are possible? So what are the solutions to this equation? Well, this is just a quadratic equation, so we can find its solution using the quadratic formula. So quick recap on the quadratic formula. Let's see if I can remember what that is. So the quadratic formula tells us if we have the quadratic equation as squared plus bs plus c is equal to 0, the roots or the zeros of this equation are given by s is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So to find the zeros of this equation, and hence the poles of our system. We just need to substitute into the quadratic formula. And doing that shows that our pole locations are given by minus b, so b is just minus 3 minus k1, plus or minus the square root of something enormous, which is minus 3 minus k1 squared, so that's b squared minus 4, a is equal to 1, and c is equal to this horrible thing, so minus 10 plus 2k1 minus 4k2. And all of that divided by 2. So by picking different values of k1 and k2, we can push these solutions around, but what locations are possible? So let's simplify the question a bit. So depending on what we pick for k1 and k2, we'll always get something of the form of alpha plus or minus the square root of beta. And how can we visualize the location of these points? So let's draw a set of axes to represent the complex plane. And now we've got two scenarios, the first in which beta is positive and the second in which beta is negative. So maybe the positive case is slightly easier. And so in that case, well, if I denote that length by alpha, and then to alpha I add or subtract the square root of beta. And so let's say the square root of beta looks like that, and we would get minus the square root of beta that looks like that. And so we'd get two pole locations here and here, say. So this distance here is given by 2 times the size of the square root of beta. So that's what, if beta is positive, for different alpha and betas, we always get 2 real roots, and by making beta bigger or smaller, they get pushed further apart or closer together, and alpha determines the center of mass of the 2 poles. So that's the positive case. And if beta is a negative number, we get a similar looking thing, but with complex solutions. So now, rather than shifting our location to the right and the left using beta, we shift it up and down. So this distance in the complex plane is given by the size of the square root of beta, and similarly in that direction. So if beta is negative, we get a pair of complex conjugate poles where the size of beta determines the size of the imaginary part, and the size of alpha determines the size of the real part. So what values of alpha and beta can we achieve by picking different values of k1 and k2? Well, we see that by picking different values of k1, we can actually make alpha equal to whatever we like. So we're able to shift either this pair of conjugate poles or real poles freely left and right by picking k1 appropriately. We can make alpha equal to whatever we want it to be. And how about beta? Well, we notice that we've got a k2 term in here. And so no matter what k1 is, we can always find a k2 to make the term inside the square root equal to whatever we like. And therefore we can also make beta equal to whatever we like. So we can also make the distance between the real poles, or the distance between the complex poles, whatever we like too. So in fact, the answer to our question is we can achieve almost any possible set of pole locations. The only constraint is that if we have complex poles, that they come in a complex conjugate pair. And actually, this is a general fact. Whenever the system is controllable, so whenever the pair of matrices AB is controllable, we can freely assign the closed-loop poles to be wherever we want in the complex plane, provided that if we have 1 with a certain imaginary part, we have its corresponding conjugate pole as well. And we've shown why this is true for 2 by 2. So when A is a 2 by 2 matrix, but actually this fact holds independently of the dimensions of A and B, as long as they're compatible. The dimensions of A and B can be whatever we like, and as long as it's controllable, we can place the closed loop poles wherever we want. Now let's try to work out how to design the pre-filter K-pre so that the output Y will track a step input R in steady state. So what does that mean? Well, first of all, it means that the input to our system is given by a step. So this means, so if this is a set of axes with t here and 1 here, it means that r of t is equal to 0 for negative time and equal to 1 for positive time. So this is r of t. And to track a step input means that the output y will tend to a value of 1 as time gets very large. So that would look something like this. If we draw a set of axes here, and we have a height of 1, it means that, y may do something different at the beginning, but as time gets very, very large, the value of y is going to tend to equal 1. So mathematically, this means that lim t goes to infinity of y of t is equal to 1. So this is our requirement. And throughout all of this, we're tacitly assuming that these other external signals are equal to 0. And this is in part connected to why this isn't such a good method for achieving step input tracking. And when we use integral action for this purpose, we'll find out that we can say a lot more about the system response to other types of disturbance too. But for now, let's just work out how to handle this design requirement. But to work out what this means, well, we just need to simply work out what y of t is in response to this step input here. And as we know, this is most conveniently done when working in the Laplace domain, because that will allow us to quickly work out what y is just by doing algebraic manipulations involving all the things in the block diagram. So the first question is, can we rewrite this requirement in the Laplace domain? And the answer is yes, by applying the final value theorem. So the final value theorem tells us that this limit is equal to the limit as s goes to 0 of s multiplied by y of s. So this is the Laplace transform of y of t. So in the Laplace domain, our design requirement is that lim s goes to 0, s times y of s is equal to 1. And now we just need to work out what y of s is, and we can do that with simple algebraic manipulations. So let's just do that over here. So what does y equal? Y is equal to c multiplied by x, where capital X is the Laplace transform of this x here. And what does x equal? Well, x is equal to this block multiplied by the Laplace transform of u. We're going to write that in a slightly different way because it'll be more convenient in a moment. So we can actually write that si minus a multiplied by x is equal to b times u. I've just moved this matrix inverse onto the other side. So this block tells us that x is equal to this times u, and I've just lifted this and put it on the other side of the equation. So why does this help? Because now we can write u in terms of r and x again. So u is equal to k pre times r plus k times x. So let's eliminate u. So this is equal to b, and then k pre times r plus k times x. And now we take the piece involving x and move it onto the other side, and we find out that si minus a minus bk multiplied by x is equal to b times k pre multiplied by r. And now we're very almost done. We can use this equation and this equation to eliminate x, and we discover that y is equal to c multiplied by si minus a minus bk inverse b times k pre multiplied by r. And r is a step input, so it has Laplace transform 1 over s, so we can put 1 over s. So this is our expression for y, and now we just need to substitute this into here and work out what k pre must equal. So we can sort of spot a few things. So this 1 over s is going to cancel with this s here, and taking the limit s goes to 0 is equivalent to just setting the remaining s, which is just here, is equal to 0. So this requirement simplifies to c multiplied by minus a minus bk to the minus 1 b k pre is equal to 1. And if we just rearrange this a bit, we get a formula for k pre. And so doing this, we find that k pre is equal to minus 1 over c a plus bk to the minus 1 b. And if we choose this value for k pre, then we'll get perfect steady state tracking of a step input r. So let's just give a numerical example of this to make sure everything's clear. So an example illustrating the computation of the pre-filter k pre. So let C be given by this matrix here. Design a pre-filter so that the transfer function from r to y is equal to cy from example 1 can track a step input. So let's just recall some facts from example 1. Well, in that example, the A matrix was given by 1, 4, 3, 2. The B matrix was given by 1, 0. And the state feedback controller that we found had entries -5 and -5.5. And that is all we need, in fact. So we just showed that k pre is given by minus 1 over c a plus bk to the minus 1 b. So to answer this question, we just need to compute what this thing is. So let's start with a plus bk inverse. Well, a plus bk is equal to 1, 4, 3, 2 plus b, which is 1, 0, multiplied by k, which is -5 and -5.5. And this whole thing is equal to, in the 1, 1 position, we have 1 minus 5, which is -4. And then 3 plus 1 times -5.5, which is -2.5. And then this is 0 and 0 here, so then we just keep 4, 2 along the bottom. And we need to find the inverse of this matrix. So we need the inverse of this, so we need the inverse of this, so we need the inverse of this. So how do we find the inverses of 2 by 2 matrices? Well, there's a formula for that too, but I always forget what it is, so let's try and remember. So a general 2 by 2 matrix might have entries A, B, C, and D like that, and its inverse is going to involve the determinant So we're going to have 1 AD minus BC. And then we have to, yes, we just have to swap those two entries. So D, and then put minus signs here. Minus B, minus C, A. So this is the formula for the inverse of a 2 by 2 matrix. And we just need to apply it to the particular matrix that we have here. So this matrix inverse will be equal to, well, the 2 comes up here and the minus 4 goes down there, and then we flip the signs of the 1, 2, and 2, 1 entries. So 2.5 and minus 4. And then we have to divide that whole thing by the determinant, which I haven't really left space for. But what will the determinant be? So minus 4 times 2, so minus 8, minus 2.5 times 4. So 4 times 2.5 is 10. So that whole thing is going to be equal to 2. So the determinant is 2. So this is the matrix A plus B K inverse in this case. And to round things off, we just need to find out, we need to multiply by C on this side and B on this side. So we need to compute 1 minus 1, all multiplied by 1/2, then the matrix 2, 2.5, minus 4, and minus 4, and B is 1, 0. Oh, I was supposed to close some brackets there. So we just need to compute what this thing is. So let's do it in steps. Let's work out what this is first. Well, this is just given by 2 times 1 plus 2.5 times 0. So that's 2. And then minus 4 on the bottom. We've still got our factor of the half. And we've still got the 1 and the minus 1 like so. And so this is equal to 2 plus 4, which is 6 over 2, is equal to 3. So C, or this product of matrices here, is just equal to 3. Therefore, K pre, the solution to our question, K pre is equal to minus 1 over 3. Easy peasy. Today we've covered our first control system design method, that of state feedback. State feedback controllers can be designed in the very special situation in which the entire state of a state space model can be measured. In particular, we've shown that by designing a matrix K, we're able to place the closed-loop system poles in whatever configuration we like. We achieved this goal by first coming up with a polynomial of the form s to the n plus a1 s to the n minus 1 and so on, which has zeros in the locations of our desired poles. In particular, we focused on the case when these were Butterworth polynomials. Then all you have to do is take the polynomial det si minus a minus bk and match coefficients. To do this, the first thing you needed to do was work out the dimension of the matrix K and assign variables to each of its entries. For example, if K is a 1 by 2 matrix, we would rewrite K in terms of K1 and K2, where K1 and K2 are specifying the individual entries of the matrix K. We then multiply out this matrix in here before determining its determinant, and then using the design freedom in the parameters K1 and K2, you make sure that the coefficients in the polynomial on the left match the coefficients in the polynomial on the right. In addition to the pole placement problem, we also worked out how to design a pre-filter K pre so that the output of a system will perfectly track a step input in steady state. To do this, we discovered that if we set K pre is equal to minus 1 over C A plus BK inverse B, we'll achieve our desired step input tracking. And that's it. You've mastered your first control system design method. Thank you for sticking with things this far. Next time we will investigate the problem of observability. So see you there.